to learn. Today I will be discussing a problem which I have made in the class earlier in earthquake engineering. Calculation of design seismic force by dynamic analysis method. This problem is being solved already by both the methods. We have 1, 2, 3, 4, 5 columns. 5 into 4 is 20. So we have 4 rows, 20 columns. How to analyze by equivalent static method and response spectrum method by ETABS. Now, for the building, the dynamic properties such as natural period and mode shapes for the vibration in X direction have been obtained by carrying out free vibration analysis. This building, the data are being discussed here. This is a 4-storied building and it is an office building. Type of constructions are there. It is majorly used for importance factor while calculating the seismic force as shown in the figure. You can see the center to center distance between the column is 5 meter both in X and Y direction. You have 4 number of bays here and 3 number of bay. This is the figure. The building is located in Shillong. It is classified as seismic zone 5. The soil conditions are medium stiff and the entire building is supported on raft foundation. Medium stiff in the sense case 2. There are 3 cases for soil. Case 1 is stiff soil and this is medium stiff and loose soil. You have 3 types. RC frame are infilled with brick masonry. Here in this case you can see only the framed structure here. When we are doing analysis in ETAB, what we do is all the infill walls as a dead load and which is being distributed in beam, or we can take the load and distribute in the slab, and this slab load will always be taken by the beam. Hence you can directly distribute the load in the beam as UDL, or the wall load can be combined into the slab dead load. So this is one of the method which we can do. And here the lumped weight due to dead load is 12 kilonewton per meter square. And it has been understood that this brick weight is being converted to dead load on the floors. So these are first floor, second floor and third floor. In all the 3 floors, this dead weights are being distributed including the self weight. So they have not considered the self weight. When we are doing dynamic analysis, the self weight is neglected. We will be only taking whatever load is acting on the structure. Hence, we will be taking 12 kilonewton per meter square on the 3 floors, and on the 4th floor 10 kilonewton per meter square on the roof. This is the dead load. The floors are to cater a live load of 4 kilonewton per meter square on floors. First, second and third floor have 4 kilonewton per meter square and 1.5 meter square on the roof. This is acting on a slab per meter square. In this slab, we know that this is a 5 meter by 5 meter slab per meter square. 5 into 5 is 25 meter square. For every square meter, it carries 1.5 kilonewton in the top floor. Now determine the seismic load on the structure as per new code. And the manual analysis is being done and you can check in the previous link. Now let us solve by ETABS. When we are opening the ETABS, model initialization, and steel section as Indian, it's been followed by IS 800, and the concrete design can be done by IS 456 2000. Press OK. We can customize this grid. Here we are having 1, 2, 3, 4 rows, 1, 2, 3, 4, 5 columns. All are 5 meter distance. 5, 10, 15, 20. Currently we got 1, 2, 3, 4. 4 number of column. We need 1, 2, 3, 4, 5. So we can introduce a new column for 25. Now in row direction we have 5, 10, 15, 20. So we got our frame here. The story height, next we can provide. First floor height is 4200 mm, rest of them are 3200. Base to first story is 4.2, 3.2 and 3.2. Yes, each and every floor we have given the height. Let us press OK. We will get our structure here. Now we got our coordinates. Now let us first assign the material properties. Add new material. We are designing according to Indian standards. First let us add concrete and let us provide M25 grade for concrete. For M25 the default values are given. Since we are neglecting the self weight, we can assume weight as 0. So in this problem you can see there is no self weight considered. When we are doing a dynamic analysis, self weight will be neglected and whatever the applied load is there, this will only be considered. Substituting 0 as the weight, even though the material is assigned, it will be not having any weight. This is one of the method to model. Then let us add a rebar TS415 grade. For this also we shall provide the density as 0. So we have assigned both of them. In this problem they have not mentioned the material, which grade of concrete, which grade of steel, these are all not considered. We will be taking this for analysis, and since we are providing 0 as the weight, it will be not having the self weight and it has only the shape of the structure. Let us design the beam and column size. Add a new property. Now here in the problem they have not given the dimensions of the column. We shall assume a section for beam. Let us assume 437 by 437. How you arrived this section in the sense? This is a trial and error method where you can get the exact dimension in order to match with the given data. Here you are not having any data of what is the size of beam and what is the size of column. Generally, when finding the mode shape, we will be considering only the bare frame. So this bare frame, and we will be assigning a weight in each and every floor. What we can do is we can take 12 EI by L cube. So this is the formula. For each and every column you can use this. One end is fixer and other end is free. So E is Young's modulus, I is moment of inertia, divided by L is the height of the column divided by cube. So how many columns are there? You have 20 columns. 4 into 5. You have 20 columns. You can multiply by 20. You will be getting a single column. And above the single column you have a weight. So this weight is, we have already arrived that. Here you can see while doing this problem we have already derived. You can check this link, and for each and every floor you have a weight of 4200 kilonewton, and at the roof you have 3000 kilonewton. So totally 15600 kilonewton is the load. And when doing the seismic analysis, it has been mentioned that the floor load is being taken as 50 percentage in case of live load, and for the roof there is no live load is being considered. We can provide the depth and width as the same. We are assigning only for beam, and let us provide the grade of 415, and whatever might be the cover is given, let us take the default cover, and it is an M25 grade concrete. Beam is being assigned. Now let us assign a concrete column which is having a size of same 437 by 437. So if we are assigning like this, we will be not having any difference in K. Here in this problem they have not mentioned any K value. K is called stiffness. So stiffness depends on the member properties. Here it is not mentioned as K in different form. You can take stiffness for each and every floor as same. K1, 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 K1. There is no K2 or K3 because the column is having the same size, and every material property is same for beam and the column. So that if you match with that, you will be getting a structure which is evenly having a stiffness. And whatever is default they have given, we are not going to design. Anyhow, we will be providing this rebar section. M25 grade concrete we have given, beam and column is being assigned. Now we have to provide the floor load. Here in the given data they have mentioned that 12 kilonewton per meter square or floors. Generally when doing dynamic analysis, the slab is not considered. The slab is considered as infinitely rigid. When a structure is undergoing practically, the structure will not be infinitely rigid, it will bend according to the force which is being applied. In this problem also, when we are understanding the theoretical problem and a real structure, there are some differences. So for understanding, we will be using, there is no slab and the slab is infinitely stiff. If we are taking the same into the ETAB model, in ETAB what you can do is you can make the slab as rigid, semi-rigid. You can provide diaphragm. By using this you can change, but in the theoretic analysis you don't have this case. So we will be assigning the slab, and let us assign a new property for the slab. So slab 200. You can provide according to minimum stiffness, according to serviceability and strength limit state. And since we are not including the self weight, what you can do is instead of shell thin, you can assume it as membrane. Membrane means it is a fabric. It will be considered as a fabric. Slab parameter is not being considered in dynamic analysis. Hence, we are providing the slab as membrane. So here you can see the column property for all the stories. we can provide the column. It's a simple way where you can provide for all the columns in a object using grid. So you can draw with this. Similarly, the beam. And for all the floors, the beam is been assigned. Assign the slab. We have provided the property of slab called slab 200. So let us assign for each and every way. Now, here you can see at the bottom also you have floor. Let us delete the floor at the bottom. Let us go to base, and for only one story, whatever we are selecting, let us delete only the floor on the base. Now we got our structure. First floor, second floor, third floor, and this is the fourth floor. Now let us provide the supports for the structure. Assign. This is fixed, and let us apply the end conditions. And now we have assigned the fixed end condition. The restraints are being assigned at U, X, Y, Z. Under three directions it cannot move, X, Y, and Z, and the rotation is also resisted. So we have provided the restraints. Now let us provide the dead load and live load. Define load patterns, the self weight, and hence we shall provide the dead load as 0, and we are providing super dead load, which consists of the slab weight and whatever the masonry weight, etc., as super dead load. And it has been mentioned here the self weight multiplier is provided as 0. Now it doesn't have self weight, even though the self weight also is considered into the dead load, so hence we are not providing the self weight. Now let us provide a live load. We already have live load for floor. There are two types of live load for floor and live load for roof. So we are having two types of live load here. Dead load due to lump is 12 kN per meter and 10 kN per meter, and live load for floor is 4 and roof is 1.5. We can provide a seismic load. For seismic load, let us do equivalent static load ESL method only in x direction. So this is the x direction, and only in one direction we are providing the seismic force. So this is being applied with respect to IS 1893-2016. Let us add this load. Let us add another load called response spectrum. Response spectrum analysis is being done in the x direction. You can see modify lateral load. We have to apply only in x direction. The earthquake load is applied in x direction only without eccentricity. We have 4 stories and the bottom is base. Here you can see seismic zone is 5 and we have applied seismic zone factor. For seismic zone 5 you have Z as 0.36. So 0.36 we have applied. Soils type is type 2. Soil condition is medium stiff and the entire building is supported by raft. So medium stiff in the sense, here you can see for using equivalent static method you have this, and when doing manual analysis I have discussed for medium stiff condition you have the case. So this is the second case and third type. There are only 3 types. Response reduction is 5. Response reduction factor, since this is a RC building with special moment resisting, hence it is taken as 5. Building is required to provided with moment resisting frame as per IS 13920. That means this is a special moment resisting frame. If the design and detailing is provided according to 13920, it should be considered as special moment resisting frame. Ordinary frames can be used when you are not following 13920 and normal detailing is done. Now, this is 5 and importance factor as 1. You can see this I. For all other building it is 1. What is the type of building is? This is an office building. Concrete office building. So office building will not come under these 2 cases. Important structures, you can read all the structures here. Telephone exchange, hospital buildings, and if it is particularly mentioned in the problem you can use 1.5. Residential or commercial building it is 1.2. If it is not mentioned anywhere here you have to take it as 1. Hence it is taken as 1. And here you have a parameter here. Determination of natural period. Here we are identifying the natural period of the building in x and y direction for 0.28 second. So if you want to build or compare this same theoretical analysis, you can use the natural period as 0.28 seconds for equivalent static analysis. Our purpose is to find the theoretical versus same thing, how to do the same problem in ETABS. So this problem is being solved by considering earthquake load in x direction of 0.28 seconds. So we will take user defined as 0.28 seconds. If it has been program calculated, it will take the IS 1893 2016 guideline and solve. So that answer will be different. Let us provide 0.28 second. So code in x direction for 0.28 second. So we are using 0.28 second as the natural frequency. Response spectrum analysis. Here also you can modify. For this you are applying the load in x direction. Why we are going for response spectrum analysis is we need the mode shape. Before starting the problem, the mode shape is given. How to find the mode shape? The natural period. Earlier in equivalent static load, we have defined it as 0.28 according to the guidelines. But when we are analyzing dynamically for finding free vibration of a structure, we need to get the natural time period. So we got 0.86, 0.265, 0.145 as the natural time period. So we are applying only in x direction. The natural time period will be different in different direction. If you oscillate the building in x direction, it has a different time period. If you push the building in y direction, it will be having different natural period. Also in z direction, if you push the building in upward direction, it will be having different natural period. So natural period is different for each structure in the three direction. If the structure is symmetry in all the three directions, then it will be having same answer. If it is not, here you can see you are having 1 2 3 4 5 base in x direction and 1 2 3 4 4 base here. Definitely the natural period will slightly change, and we are considering only the x direction, the property of building vibration in x direction only we are considering. And we can provide the response spectra cases. This is a 4-story building. The bottom story is base, response reduction factor is 5, and according to seismic zone 0.36. And when we are substituting the zone soil condition, here it is given as the same data we can take, and for the building the dynamic properties of natural period and mode shape is being given here. And this problem also we have solved, which you can find in this playlist. And here you can see this is the time period. For this time period, SA by G they have taken is 1 by 0.86. So what do you mean by 1 by 0.86? For time period is 0.86. This is the SA by G for response spectrum method, which is given in IS 1893, and this is for equivalent static load. So our time period is in between 0.86. So here you can see 0.1 to 0.4 seconds, and next time period is 0.4 to 4 seconds, which is this case. If the time period is 0.86 second, here you can see 1 by t. T is 0.86. So 1 by t, which is been taken as first case, the rocky or hard soil sites. So in this case, it has been taken. Hence, we are considering soil type is 1, importance factor is 1, and the same case. For this we are going to do the program calculated. Note that there are two differences. When we are doing equivalent static analysis, we have given user defined and we have provided 0.28 second. Now in response spectrum analysis, here we are providing program calculated. Why? Because we need to find the natural frequency of the structure without any walls. What is the natural period of the structure? Free vibration properties of the building for vibration in x direction. There we are going to discuss how they got this value, and we will move on to the sum. Then press OK. Now, for doing dynamic analysis, it is essential to provide mass source. What is the reason for providing mass sources? During a dynamic analysis, a building has to be first analyzed for static, then for dynamic case. In dynamic, it can be analyzed for wind as well as the earthquake. During an earthquake, there are several conditions which are given in 1893. During a vibration, you can only take 25% of live load. During a vibration, the total live load will not fall on the structure vertically. The major force will be horizontal. So you can reduce the live load. 0.25 for case and 0.5. You can reduce 0.5 of live load. So these cases you can verify this in the code book. Now, as far as this case is concerned, here we are going to take 50% of live load and dead load will be full. The live load in floor will be half. whatever live load is there, and you will be having a super dead load. This has to be considered during the vibration. These two will be the case. You can see there is a dead load which is being taken, and 300 is this total area 15 into 20 plus 12. So they are considering all 12 kilonewton during the dynamic analysis and zero point 0.5 times the floor load. So what are the floor loads? First, second and third. No live load to the roof. You should not add any live load roof here. So this is for your understanding. Specified load patterns. Here we are specifying what are the loads to be considered during the seismic analysis. Full amount of force in super dead load and live load in floor is half. So these two we will provide, and additional mass and elements self mass we are not going to consider here. Then press OK. So let us provide a rigid diaphragm, because in the problem we will be assigning the slab as infinitely rigid, even though we have considered as a membrane here. If you are doing, you have to take it rigid or semi-rigid according to the stiffness. Here let us assign let us select all the floor and apply this. So this diaphragm, if we are applying, we will be getting load which is acting on the center of the diaphragm. So this is the center of mass. For all the floor, the mass has been concentrated here. Here you can see the letter, and for each and every bay, this slab is splitted. Now when you apply diaphragm, this will become as a single element, and all the load will be concentrated here. When doing dynamic analysis, we will be taking lump mass. So all the mass will be concentrating here when we are applying the diaphragm, and we can get the answer as required. Now let us assign the load. So this is the first floor. We are in second floor. You can see story 2, and the third floor, story 3. All these shells we have selected, and let us assign a shell load, a uniform load of a lumped weight dead load is 12 kilonewton per meter square on floors. So let us provide 12 kilonewton as super dead load. In the direction of gravity, let us apply. Yes. In 3 dimensions, you can see first, second and third floor is being applied with the dead load, which is super dead load. Let us go to the roof. In roof, let us apply 10 kilonewton per meter. On roof, 10 kilonewton per meter square. Let us apply in this direction. Now let us apply the live load. The floor are to character for a live load of 4 kN per meter square and 1.5 kN per meter square on roof. We are in the fourth floor here. Live load on the roof 1.5 and live load on floors. Third floor. You can group this, and while doing n number of floors, and according to your project you can group all this floor like this, and in a single click you can select all the group. So since this is a small problem, I am selecting it individually for all the 3 floors except roof. We are selecting here, and 36 shells are being selected. Now we are applying live load on floor here. Yes, we have assigned all the loads. Now our problem is ready to analyze. We have considered 4-storied reinforced concrete office building. It is located in Shillong. Zone factor is given. The medium stiff is being given for equivalent static load, and for response spectrum for dynamic analysis we have given as stiff according to the given data. The supported in raft frame is infilled with brick masonry. So we have removed the brick masonry, and the fundamental period is being assigned. Here you can see the load resistance is provided moment resting frame infilled with brick masonry panels. If you are providing the walls, you can get that natural frequency in the ETAB. Now we are just comparing what we have done here. So that is why infill is being not provided in ETABS. It is being converted into the load. Lumped weight due to dead load is 12 kN per meter square on floor and 10 kN per meter square on roof. The floors are to cater 4 kN on all the 3 floors and 1.5 kN per meter square on roof. Determine the seismic load, and this is a manual analysis. This is a moment resting frame case which we are doing. Both equivalent static load and dynamic analysis we are going to do. Before starting the analysis, let us check the model for any error. Model has been checked, no warning messages are generated. So our model is good to go. Before doing the analysis, let us check live load on roof. If we are applying, here you can see live load on roof. Only in roof we have given 1.5. Live load on floor we have given in first, second and third floor. Here you can see in all 3 floors. And dead load, the self weight we have not given. Super dead load we have given for all the first 3 floor as 12 and at the top as 10. Now this is equivalent static analysis for masonry structure, and this is response spectrum or dynamic analysis. Yes, we have to define the function, response spectrum function. So according to IS 1893-2016, we are providing the response spectrum analysis. Response spectrum analysis in X direction we are doing. And what is the case for equivalent static load? We have assigned the structural characteristics, and for response spectrum method we are providing the response spectrum function. This is in zone 5 and the seismic zone factor is 0.36, importance factor is 1, and the soil type is 1. Here we are considering all the acceleration is given here. This is SA by G value is given here, and SA by G, the whole function which is being taken from IS code, and you can see the functional graph here. So this will be taken automatically and it will give the answer. So for response spectrum analysis, we have to do this. Then define model cases. Now we have to modify the shown case. Here for getting the fundamental natural period and the mode shape, we need this. So instead of eigenvalue, we can provide RIDS. Eigenvalue will provide 12 number of modes. Here you can see 12 number of modes here. If we are providing RIDS model mass case, you can provide only the required number of modes. Here we need only 3 modes. We need acceleration in only the x direction. You can see all the y z directions are there, which is not required for us. Now we only need 3 number of modes in x direction. So this is what is given here. 3 modes in x direction is only considered. Now let us press OK and define load cases. In load case, all the load cases are done according to linear static. Now here in response spectrum, we have to modify this and provide as response spectrum. So it will provide the dynamic analysis here. Or otherwise, if we provide linear static without acceleration, without fundamental natural period of all the modes, we will be getting a single answer. So we need the dynamic analysis, hence we have to give acceleration and the load in one direction, which is x direction. The function, what function we have provided? Response spectrum analysis. Currently we have provided the response spectrum analysis function, and scale factor is 9806. This is the scale factor which is being considered, and this is nothing but 9.81. Here all the values are in terms of mm. So this 9.81 acceleration due to gravity is being taken as 9.81. Instead of 9.81, it is 9801. Accurately, it is being given as the scale factor. And the model cases will be considered. Model combinations will be square root of the sum of the squares. This method we have done in theoretical analysis, hence we are doing the same. Directional combinations, we are only considering the one direction. Anyhow, let us provide OK, and model damping is for 0.05 ratio of damping, that is 5% damping we are considering. There is no eccentricity for diaphragm, hence we can press OK. Now let us start the analysis. Our system is good to go from now. It will be doing the response spectrum analysis and equivalent static load analysis parallelly. Now let us check the model information. In base reactions, we can see here. The equivalent static load in x direction, which is 1404. So this is the value we got. Base shear is VB 1404 kilonewton. This is the value for equivalent static method, and this value we got here. Fx, what do you mean by Fx is, this is the horizontal force which has been acting, and you can see the rest of the values. Now, the total load is 15,600 kilonewton. So here you can see the center of mass. 4,200, 4,200 and 4,200. Here it is given in terms of kg. So you can calculate in terms of kilonewton. Here the value is 428280. This is in terms of kg. You can convert it into Newton. You can multiply by 9.81. So this will be in terms of Newton and divided by 1000. This will be in terms of kilonewton. So you will be having nearly 4,201. So this was our load which has been provided. Here you can see 4,201. So here in theoretical analysis 4,200, and for all the three floors, first, second and third, and the fourth floor 305914. 305914. This is in terms of kg multiplied by 9.81 divided by 1000. We will be getting in terms of 3001, nearly 3000 kilonewton, which is being applied in the top floor. So whatever load we have provided, which we can see in both the directions, in x and in y directions, the mass will be the same. And this is the total mass, cumulative mass. Here you can see 15,90,757. 15,90,757. This is in terms of kg. You can multiply by 9.81 divided by 1000. You are getting 15,605. So this is our total load. This is the cumulative mass, and in ETABS we are getting 15,600. The same value 15,600 is your base shear here, and we got our base shear value. In equivalent static method, we got the lateral force, and each and every floor has the value. Let us check in ETABS. Display response spectra plot. Equivalent static analysis, and if you go to storage shear, here you can see the total base shear is 1404, and at each floor what is the shear, here you can see the value is 595, etc. Or if you need a lateral story force, you can see 595 is the maximum. This is called 595. You can see at the bottom. So this is 595. Next value is 491. At bottom you can see, here you can see the value. I am placing the cursor, 491. Next value is 329, nearly 239, nearly 240, 239, and last one is 77. Here you can see 77. All the values we got in the ETABS. So this is the way you can do equivalent static analysis in ETABS. Now let us go to response spectrum analysis. When doing the response spectrum analysis, first we should check the model for the mode shape. So this is our first, second, third mode. So let us check the mode shape here. model periods and frequency. Yes, we got our first mode as 0.861 and 0.860 and 861. Second mode is 0.265, 267 is the second mode, and third mode is 0.143. Third mode is 0.145. So nearly we got around 95-97% of the value as the natural period in first, second and third mode. And when we are looking into mode shape, how to get the mode shape in the ETABS is deformed shape and press the mode. If you apply, you will get the first mode. Yes. Here you can see this is the first mode. With respect to the ground, you can see there is a displacement. In first mode, all the values are here in terms of displacement. Ux, can you see Ux is minus 0.013. So let us write here. Our first value is 0.013. Second value 0.023. Third value 0.029. And fourth value is 0.033. Now let us go to the second mode. Mode 2. Let us apply. Yes. Now we got 0.030, 0.030, Now I am considering the right side as negative. You can see in mode 1, the mode 1, all the values are in terms of minus. You can see minus, minus 0.23, minus 0.29, minus 0.33. We are considering the left hand side as the first mode. Always mode 1 will be in positive when we are doing theoretical analysis. Same we shall do it. And whatever is in right, we will be considering it as negative. So minus Ux here is 0.030. We will be considering as minus 0.030. And this is minus 0.025. Minus 0.025. Next, this will be plus 0.006. And next value is 0.033. 0.033. Now let us go to the third mode. Left hand side is plus 0.034. Now this is minus 0.022. And this is minus 0.017. last value is plus 0.024. Now we got all the raw data. These are all called displacement. So what do you mean by mode shape is with respective to roof. What is the displacement in each and every floor? This is what been taken here. Now we know that this is roof, this is second, first, and the ground. Now let us find the mode shape value with respect to roof. When we are dividing this value, we will be getting the mode shape. So for roof to the third floor, you have to divide 0.29 divided by 0.033. The floor, this we are taking it as 1, and this value is 0.88, 0.696, which is 0.7 we shall take. 0.7. This is the way to get the mode shape. Similar values you can see. There are some deviations. The model mass participation factor is 92.6 in first mode, second mode 6, and third mode is 1. Let us check the model participation factor. Yes. 91.912. This is the model participation factor. 91% of mass is concentrated in first mode. In theoretical value, we got 92, and for mode 2 6. Here we got mode 2 as 7, and mode 3 as 1.5, 0.015 into 100. If we make it, you will be getting in terms of percentage. So it will be 1.5 percentage. Here we are getting 1 percentage. So this is the model mass participation factor. Now the value, final value of base shear is 610 kilonewton. In base reaction, we can see total base reaction is nearly 610.18, and we got 610 here. Due to the model change, here you can see the value what we derive due to theoretical analysis is we will be multiplying with mode shape Q and this V value. Since our mode shape values are slightly different from the theoretical answer, we will be getting some deviations, but the overall answer will be nearly same. Due to the lack of insufficient data in theoretical analysis, we have assumed nearly whatever is being given in the theoretical given value, and we have started proceeding the problem. So this is the idea which you can get from the ETABS analysis. Here you can see, yes, the response spectral analysis shear. For each and every floor, what is the lateral load? We can see here 610 is the base load, and here we got is 610. Next is 510. 514 is the value what we got from ETABS, and 371 378. This value I have told, there is a slight change, 182 in V4 and 186. So this slight change, this due to the assumptions. We have assumed that the column and beam with their grade of concrete and all the properties which are not provided in the theoretical analysis. We have assumed according to the experience, and we can nearly match this. So if we are doing iterative analysis, we can match exactly to whatever answers we get. Our motto is to make you to understand that what we are doing in theoretical analysis, we can get into the ETABS. And finally, we have lateral force. Lateral force in Q1 is 610 minus 510 is 100 kilonewton. 610, 514. First value is 96. In theoretical, we got 100. Second value is 139. That 139, 514 minus 378. 136 is the value we are getting. And here we got 139. Third value is 189. 378. 378 minus 186. 192 is the value. I am rounding it off. Approximately we will be getting 189. We got here we got 192. I hope you enjoyed this session. Engineering is a practice. See you soon. Happy learning.